So in this video, we're gonna look at the graph of a function and its inverse. So there's two important points that you need to know. And the first point is that f and f inverse, if you look at the graphs, their graphs are reflections over the line y is equal to x. So basically, if you have the point f, so if you have the coordinates xy on your function f, then on your function f inverse, that point is gonna go to yx, right? So if you have the input x and your output is y, then putting that output as your input for your inverse function gives you the output x, right? That is the definition, the concept behind inverse functions that we've learned. And these 2 points are reflections over the line y is equal to x. And this will become clearer as we look at more examples, right? And the second point is that if a function is self-inverse, then, so basically when I say self-inverse, that means f is equal to f inverse, right? Then the graph of f itself is symmetrical over y is equal to x. So these are the 2 points that you need to remember. So if your function is self-inverse, then the graph of f itself is symmetrical over y is equal to x. And if it's not self-inverse, if you have a function and its distinct inverse, then what's going to happen is the graph of f, if you reflect it over the line y is equal to x, you're going to get the graph of f inverse. Alright, so that is about it, and I think that is all. In case I missed something, I don't think I did. So I'll mention, in case I do miss anything, I will mention it. Alright, so those are the 2 important points that you're going to want to remember in this topic. Alright, with that being said, let's go and do some questions. Now, question 1 tells us, on a copy of each grid, draw the graph of f inverse if it exists. For the inverse function to exist, we want the function to be 1-to-1. And for a function to be 1-to-1, it must pass the horizontal line test. So D does not pass the horizontal line test, right? If you draw a horizontal line, it intersects the curve at 2 distinct points. This function is many-to-1. That means this is not invertible. So D, no inverse. So we are going to work with A, B, and C. Alright, so let me turn on my laptop real quick as well. Okay. So if you're given a grid and you're asked to draw the graph of f inverse, we're going to use the first point that we learned. So draw the line of y is equal to x, right? You want to draw this. So y is equal to x. So whatever x is, that is going to be y. If x is 1, y is 1. If x is 2, y is 2. If x is 3, y is 3. X is 4, y is 4. And so on. So it makes a 45-degree angle relative to the x-axis. So let me just draw y is equal to x with this dotted line. Alright, so this dotted line is y is equal to x. And now we want to use, if you have xy for f, then that is going to change to yx for f inverse. And you're going to see that this point is basically a reflection over y is equal to x. So let's take an example here. You have 1, 0. This is going to change to 0, 1. So you go to 0, you go to 1. You have 0, 1 here. Right? So 1, 0 is on f. So 0, 1 is going to be on f inverse. Similarly, you have 3, 1. Right? This point is 3, 1. So 1, 3 is going to be on the graph of f inverse. So 3, 1 is on f, so 1, 3. So 1, 3 is on f inverse. Similarly, 5, 2 is here, so 2, 5 is on f inverse. And basically, so this y is equal to x and f intersect, so this point has to be on both f and f inverse. And then you can just continue. So you have negative 3 comma 2 on f, right? Negative 3 comma negative 2 is on f. So negative 2 comma negative 3 must be on f inverse. And I believe this point should be on f inverse. So your graph of f inverse looks something like this. And if you think about it, this red graph is a reflection of the blue graph over the line y is equal to x. All right. So we are done with part A. So it's the red line. The red graph is going to be f inverse. All right. For B, we use the same method. Now you can draw y is equal to x. Flip over some points. Alright, so now let's just flip. So because this point lies on y is equal to x, it's going to stay there. You have minus 4 comma 2, so you're going to get 2 comma minus 4. Alright, and you have 0 comma 4, so you're going to get 4 comma 0. So it's going to look something like this. The reflection is going to look something like this. Alright, so that is going to be f inverse. So for D, there is no inverse because f is not 1 to 1. So for C, you do the same thing. You draw y is equal to x, which is going to be the diagonal, right? You plot the points. So remember, you have to be careful with your axes. I can only draw it like this because I know I have on my axis. So you want to plot some points. Y is equal to x. Whatever x you choose, that has to be your y. So if you choose x is 1, y is 1, x is 2, y is 2, and it's going to be a straight line with a slope of 1. All right. So now we take some points and we plot it. So 0 comma 3 will correspond to 3 comma 0. So this is a point. If at towards 6, right? If you take x is 6, you have output 0. So towards 0, your output is going to be about 6, right? And let's see. This point is going to stay the same because it's an intersection. So now you have to sort of visualize how it's going to flip over. So I have to flip over this part. So this part flipped over is going to look something like this, I believe. And then the lower part flipped over is going to look something like this. So if I draw it more carefully, if you flip points over more carefully, then because this part is quite symmetrical, right? It's quite symmetrical over the line y is equal to x. So this middle range is going to look sort of the same. So you actually are going to have something like this. Something like this. That's yeah, approximately how your inverse function is going to look like. Or you could just plot some more points. So about these points are going to flip about and be exactly as they are. So you have 2 comma, let's say 0 0.6. So you go to 0 0.6-ish and you got to plot to 2, right? So this part is about the same. You have about like 0 0.2 comma 4. So 0 0.2 comma 4, you're going up. And then you have like 5 comma 0 0.1. So 0 0.1 comma 5. And then you want to connect these points. So just approximately, I'm guessing the points. So your inverse function looks something like this. All right, that looks acceptable. So this is going to be f inverse. All right. So this is 0 0.8 comma 2. So you need like 2 comma 0 0.8. So I think it has to be a bit higher. So it has to be like go from a bit above. So maybe like this. All right, that looks better. So I think the first one was a bit too low. So you can just guess some points and figure out. All right, so this should be it for C. So you just want to flip the blue graph over the line y is equal to x. Not this one, but this one is x. All right, so moving on to question 2. We are given the function f takes the input variable x and it maps to 2x minus 1 for this domain. All right, so we need to find an expression for f inverse of x. So y is 2x minus 1, and if you isolate x, you get y plus 1 by 2. F inverse of x is going to be x plus 1 by 2. All right. State the domain and range of f inverse of x. Well, we know the range of f inverse of x. The range of f inverse of x is going to be the domain of f of x. And the domain is just this. So it's going to be -1 f inverse of x to +3. Now the domain of f inverse of x is going to be the range of this graph, right? So let's visualize the graph. If you visualize the graph, your graph looks something like this. This is a linear function. Slope to y-intercept is -1. So if you put -1 into this function, you get -1 comma -3. And if you put +3, you get 3 comma 5. All right. So that means the range of this function is from -3 to +5. So that means the domain of this function is -3 to +5. All right. So we have range and we have the domain. And it says, all right, so we're done with A and B. And part C says, sketch on the same diagram the graphs of y is equal to f of x and y is equal to f inverse of x, making a clear relationship. All right. So I don't have my coordinate axes. Let me find my coordinate axes first. I probably have it somewhere. Okay, I have it here. So I'm going to duplicate, I'm going to cut, and I am going to paste it here. All right. So now let's go here, and we are going to plot 2x minus 1. So if you plot the graph of... So first, let's plot y is equal... Sorry, I'm in the highlight. Okay. So y is equal to x is going to be here. All right, so this is y is equal to x. Now, our given function was 2x minus 1. So 2x minus 1 looks something like this. Sorry, not there, here. So I hope I can draw a straight line. Somewhat, all right. So this is f. And now I need to draw f inverse of x. So f inverse of x has a slope of half and a y-intercept of... So I can write this as half x plus half, right? So my y-intercept is positive half. My y-intercept is positive half. And my slope is half as well. All right. So I go 2 units here and 1 unit to the right. 2 units. So, yeah. So slope of half means I go 2 units positive in the x direction and 1 unit up. So 2 here, and then 2 units here, 1 unit up. 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 So something like this. 2 units, 1 unit down. 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 So my graph of my inverse function is going to look something like this, right? This has to be a reflection. This is going to be f inverse. And f inverse is a reflection of the graph of f over the line y is equal to x. So on my graph, I have the point 6, comma 11, I think. Yeah, 6, comma 11, so I should have 11, comma 6 should be on the graph. And it is, right? You can see that it is going to be on the graph. All right. So we are done with question 2. So this is how the graphs look like, and basically the graph of f inverse of x is a reflection of the graph of f over the line y is equal to x. All right. So I want to keep my diagram in case we need it later, and I'm going to erase here. So we're done with question 2. Question 3. The diagram shows the graph. Shows the graph of this function. So state the range of f. So obviously, if I put 0, then that's the maximum point of the function, and it's decreasing as x tends to infinity. So if I put 0 here, f of 0 is equal to 2, right? 4 divided by 0 plus 2 is 4 divided by 2, which is 2. So f of x is less than or equal to 2. That is the range. And it's going to be bigger than 0, right? So if you pick a very, very, very big x, then it's going to get closer and closer to 0, but it's never exactly going to be 0. So that is going to be the range of your function. Now find an expression for f inverse of x. So we have y is equal to 4 over x plus 2, which gives us xy plus 2y is equal to 4, which gives us x is equal to 4 minus 2y over y. So I did it very quickly, but you can get the expression that f inverse of x is going to be 4 minus 2x over x. So that is going to be... Now, I know the domain of f inverse of x, right? The range, I know both of these. The range of f inverse of x is going to be the domain here of f of x. So it's going to be f inverse of x is going to be bigger than or equal to 0. That is going to be my range of f inverse of x. The domain is going to be the range of f of x. So domain is going to be... So the domain is going to be this expression. All right. On a copy of the diagram, sketch the graph of f inverse of x, making clear the relationship between the graphs. All right. So you want to draw your... y is equal to x, right? So if I have 0, when my x value is 0, my y value is 2, then when my y value... If I have 0, comma 2 on my f graph, then on my f inverse graph, I need to have 2, comma 0. So 2, comma 0 is approximately going to be here. This is where it intersects. And it's going to approach asymptotically the y-axis. So you can see that this graph is quite easy to reflect. So the graph is going to look something like this. All right. So this is going to be f inverse. So we are done with 3. And 4 is very simple as well. So 4 just says, find an expression of f inverse of x, and hence decide if the graph of y is equal to f of x is symmetrical about this line, right? And that just means check whether f is self-inverse or not. So question 4 is asking us to check whether it's talking about the second point. If f is equal to f inverse, then the graph of f is symmetrical, or a reflection itself over y is equal to x, right? So we just need to check for self-inverses. So I'll check A and D for you, and I'll leave B and C for you. All right, so A is f of x plus 5, 2x minus 1. And now I can say y is equal to x plus 5, 2x minus 1. If I multiply by 2x minus 1 on both sides, I get 2yx minus y is equal to x plus 5. And I get 2yx minus x is equal to 5 plus y. And finally, I get x is equal to 5 plus y divided by 2y minus 1. And f inverse of x is going to be 5 plus x, 2x minus 1. Which is exactly what we started with. So A is yes. It's self-inverse. Therefore, it is going to be symmetrical about y is equal to x. So D is 4x plus 5, 3x minus 4. So you get 3xy minus 4y is equal to 4x plus 5. You get 3xy minus 4x is equal to 5 plus 4y. You get x is equal to 5 plus 4y divided by 3y minus 4. So I know I'm doing it a bit quickly, but I am hoping that you're going to try the algebra on your own. And that is exactly what we started with. You get f inverse of x is 4x plus 5, 3x minus 4. Therefore, yes. It's a self-inverse, and self-inverse means it's symmetrical over y is equal to x. And we are done with this topic.